another session. We last talked about we introduced losses in optical fiber, and I described or defined the loss in terms of change in width and the change in amplitude. We talked of bandwidth increasing, decreasing. We talked of detection. We mentioned use of repeaters to deal with amplitude here. For width, time duration, what can we do? All right. I was saying for width Apple, participants can now see my whiteboard. Okay. Ish width in a decrease. Amplitude, I mean. And we said we have a solution for that. We use my repeaters. Go above. What do you do? Broadening width, changing width. What can be the solution for that? Anybody? What can be the solution for that? I was expecting these sessions to be discussions. When my notes, just referring to your notes, with cheaper width, and you ask questions. But no one is asking questions. My notes video. I don't know. Ways the easiest way for me, take notes. Paper something is really important. So that when I ask my questions like this, you just go refer my notes. You understand? How can we cater for you here with you? How can we do that? Up. My repeaters, they wake. But with that, don't have a problem. My repeaters, you are. How can we cater for that? Nope. No one knows. No one knows. But it's not to pause broadening. Long story short, open up integrated index optical fiber. We will get there. I just thought someone will intervene on the all right. Loss of length L. If you're given an optical fiber of length L, loss of length L. If you're given an optical fiber of attenuation of length L, we have what we call attenuation. Decrease in amplitude, decrease in power of that signal. The power, the transmission should be close to the power at the receiving end. If it is less or far less than the input power, we talk of attenuation. Signal power is being attenuated, that is loss. How do you calculate attenuation? That attenuation in an optical fiber of length L. We have a formula, loss in decibels. It's 10 log input power over output power. So if you're given an optical fiber, calculate the attenuation in that optical fiber. What do you do? This is the length of your optical fiber. This is the transmission side. This is the receiving side. What is the attenuation of that optical fiber? With power in. Receive a light with power out. You calculate the length of the optical fiber L. There's a power in, power out. Where is the length? Oh, the length is not yet there. So if you want to calculate the loss, there's a power in, power out, 10 log, and you find your answer in decibel. Simple mathematics. What is the loss in a given optical fiber? Log input over power output. Now, that is loss. We have what we call the loss coefficient. We have what we call the loss coefficient. To calculate my loss is I. The loss coefficient alpha, it is equal to the loss decibels over the length of the optical fiber. L. So now I'm going to calculate the coefficient. This is 10 over L log P in over P out. Simple mathematics. We can calculate the loss, which is this. We can calculate the loss coefficient, which is that. My units, this is now dB per kilometer. Units. My units, they are very important in this course. You need to know my units. Not my, what did we call those? Meter, second. What did we call those? Meter, second, a temperature, degree, Kelvin, I think. Time, distance. I don't see my units. I think I say in like pressure. That's my pressure in a Pascal. Weight in a kilogram. Gram or a kilogram, I don't know. What do we call these units? The more I refresh. My gosh, that first year is my practicals. Standard. And that's my year. S units. That's my G. Anybody? What do you call my units? My primary units. That's my G. Yeah. Look for it. SI units. And that's my SI units. Thank you very much. I'm going to lose John. My SI units. Standard G. International. What does SI stand for? I don't know. Right. My SI units, you need to know how to use my units in this course. Not necessarily my SI units. Je nous ai my units that don't need to be turned to my SI units. There are specific units and by, for example, dB per kilometer. SI I gonna go that and then it's a dB per meter. But in here I'm saying we calculate them in dB per kilometers. It's very important to bata my units attributions dB per kilometer, not dB per meter. Right. You see importance of this partial calculator, my dispersions, my intermodal dispersions, and all. Right. So this is the loss coefficient dB per kilometer. You need to know conversion of decibels to decibel meters. How do you convert that? How do you go from decibel meter to decibel or vice versa? Anyone? Very more video. I explain this. I need someone who will tell her. Or I'm going to stop doing these intermediate complementary videos because when I'm squaring. If you feel with this and those you are wrong. Because I'm just summarizing a lot of things here. Someone tell me, how do you convert that? How do you make that conversion? Decibel to decibel meter. Nope.
Convert a power from dB.
Conversion dB to dBm. How do you do that?
It's power in dBm. In dBm is equal to 10 log power in milliwatts.
Thank you very much. Who is that?
Momberume.
Johnny. Momberume Johnny.
Matthew
Momberume. Johnny then Mombe short. Yeah.
Yes.
Momberume. Exactly. Satara na Momberume is also. Power in dBm is 10 log power in milliwatts. So that is correct. Can I name watts? You can calculate dB, 10 log power. no dB. Can only milliwatts. You can calculate dBm. A lot of questions, they'll be involving this conversion. Dokupa power in, Dokupa power out. Do you calculate loss in dBm? Iyo nungo akaperi kumawatsi, iyo akaperi kumawatsi. Pasika ukanoplaga zvine papapo zvisirizo. That is zero. And you come out confident. There is a conversion which needs to be done from a dBm and my dBi. I think I gave an example in my videos. That's why my videos are repo. Now it's just to highlight, you need to understand this. Right. We are done. We have what we call my loss mechanisms. This is how loss happens. Loss mechanisms. We have absorptive. You need to know this definition. Absorptive loss. It is two types. Intrinsic, extrinsic. Define those two. Doma no samafana munao wakagara tikuita lesson kudai so unongonoverenga zvawakanyora. And I feel like vanhu vari kuziva, but if you don't do that, we have problems, issues, big issues. What are intrinsic loss mechanism? What is the intrinsic, extrinsic? Define that. Anybody?
These are lost by primary constituent material of optical fiber.
Lost by primary constituents. And the other one?
Is these are losses due to absorption of impurities.
You do that in an exam, you have 4 marks. As cheap as that is. 2 marks first definition, 2 marks second definition. You need to know these things. Intrinsic, extrinsic. We have radiative. Someone mentioned that. We have radiative. Radiatives near relay scattering. You need to know my definition of all these things. Relay scattering. We have Fresnel reflection. Right. You need to know my definitions. I'm not going to ask anyone else. Right. But relay scattering. Yes, Panado respond. Thank you very much. Respond. Relay scattering. Yes, go on. You know, see?
Scattering.
Spelling. MIE. MIE.
Then scattering.
What is that? I've never heard of this one.
Seriously.
Yes, seriously. Then the memory photo. As in my optical fiber, but then I tell is it?
All right, yeah, the memo by the phone is.
All right. As not the my optical fibers memory.
Out with them.
You work with them. What is my scattering? Please educate us.
That's what time was up.
Yeah. Wakangano. Okay. This is something new to me. My scattering. Okay. I'll research on that. Possibly the next stream will benefit from memory takadis, my scattering. I'll do a research on that. Right. Relay scattering, this is caused by impurities frozen at the time of fabrication in the optical fiber. Then we have Fresnel reflection. This is due to the power reflected as the output of the optical fiber. All right, at output of optical fiber, we have something like this. Optical fiber, we're just going to deal with the core here. This is output, Rx. And maybe detector range. This is N1 core of the optical fiber. And this is N refractive index of, let's say, optical detector ring. I'm sure it's not necessarily optical detector ring wrapper, but something else. There is something with a different refractive index. So as wave where rhythm co total internal reflection require apa rinasvika apa refractive index ikangochinja zvichibaranzi papa, some light gets reflected back into the optical fiber. Some of it obviously will be refracted right on the other end, then it gets detected. But kana refractive index iyo iri dam, you have some of the light being reflected. In the light rikadzoka uku, the more light rikadzoka uku, it means kunoko detection yako inenge yakadako. Basically, that is what Fresnel reflection is all about. It can be calculated, reflected power, that's N1 minus N0, N1 minus N0, N1 plus N0. So this is my N0. The refractive index of the other material, which is on the boundary with the receiving side of the optical fiber squared. It can be calculated. A typical question, you are given all this. You are given N1, you are given N0. Calculate the reflected power, Fresnel power. Simple calculations. And this is usually calculated as a percentage. My value is 0.01. What is this? 1%. You find my values are very, very small. Then it means it is 1%. Usually calculated as percentages. All right, we have Rayleigh scattering. It can be calculated using A lambda is equals to A0 lambda 0 over lambda. What is A? What is lambda? What is lambda 0? What is A? What is lambda? What is lambda 0? Makaverenga. You need to know the difference between these so that you can calculate that. Because question for this one specifically, question I have for you, it is sort of a paragraph. The wavelength of this light is equals to chakat. Fundamental wavelength is equals to chakat. Calculate the Rayleigh scattering. If you cannot identify the fundamental wavelength, fundamental of a given light, question you will fail. So I have this, I can remember this. This is wavelength of a given light. E do Rayleigh scattering actually. Rayleigh scattering. So we got A lambda. This is the Rayleigh scattering loss at wavelength lambda. We got A 850 nanometers. This is loss at 850 nanometers. We got A 1550 nanometers. This is loss at 150 nanometers. What is A0 and what is lambda 0? You need to define this in just there. I can see this by my notes angle definition only. I don't know. I forgot. Find out what that is and make my calculations. In video sharing, A0 lambda 0. Look at A0 lambda 0. What does that mean? What's that?
You say
Yeah.
A0, I think the Rayleigh scattering loss of the fiber.
Lambda 0.
Rayleigh scattering loss of the fiber.
Well, I think we'll do example. Next time I'll come here better prepared to do the example. Or just go through the video. There's an example there. I can also calculate what you need. Very, I remember I got yes, yes, I'm listening.
Some examples, remember that lambda node, that's 850 nanometer.
Okay.
Then A node, that's 1.7.
That is 1 point.
A node, A node.
A node is 1.7. 1.7 like this.
Then A lambda, that's A bracket 1300.
Calculate. Question I got to calculate.
Then calculate you out about the loss.
Find the loss. Well,
Yeah.
yes, tower I'll go.
What are the question as?
No, I just needed the specifics. Could A lambda is a cheat? What is that? That's what I wanted. Because
A lambda, that's
it has a definition. It has to be defined. What is that? And I think formula is this correct? Up. Pana 4 paripa. No one corrected that for me. Why?
Pana
4.
yes, sir.
Why? All right. Pana don't respond.
In A lambda, that's you said is the value of loss by the relay pattern, where A is the wavelength. That's what you said.
Where lambda is the wavelength, not A.
Where lambda is the A. Yes.
Okay. We'll do example next time. A lot of things happening here. My calculations, chances what was happening really. Move, and that's way. There's no way. I believe me. That question, irregular. American identical my scattering. My scattering refers to the elastic scattering of light from atomic and molecular particles whose diameter is larger than about wavelength of incident light. Okay, we'll do a little bit more research. Then those are my scattering. Thank you very much for your input. You need to know Rayleigh scattering here and how do you calculate using this. I remember very well when I did my calculations there. Tricky, papa. Identifying what is A, what is lambda naught, what is A naught. Tricky, papa. All right. Yeah, let me leave it at that. The Rayleigh scattering loss coefficient of the fiber is 1.7 at 850. Determine the power at 1.3. Okay, let's continue. That was the question. Let's continue. Rayleigh scattering, done. Fresnel power, done. Let's talk pulse broadening. Enter pulse broadening. Definition, what is pulse broadening? What is pulse broadening? Question.
It is in the mode.
Yes.
It is intermodal dispersion in mode optical fiber.
Is it only intermodal dispersion? Yes. But that is not the definition I'm looking for. Intermodal dispersion. It's like you are answering a question with another question. What is intermodal dispersion? Pulse broadening. Question number 2, assignment number 2. What is post-broadening? What is post-broadening? What causes? What are the causes? Causes of post-broadening. Assignment number 2. Question number 2. All right. That represents post-broadening. We go to intermodal dispersion. Running out of time, 10 minutes to concentrate the intermodal dispersion. Okay? Intermodal dispersion. All right, definition. Anybody? Anybody? Definition.
It is whereby
On your upper screen, I think you can write as well. Screen you can write per screen if you want to explain. You should draw a diagram. Do that. Interact. Like with the e-learning. You need to just change the setup. My lecture rooms up. So if you're able to write something, come up front on your explanation. Yeah. Go on and get up in the.
it is whereby different race takes different paths.
Diano. Who is that? Diana Pindo.
Chief.
Chief. Thank you very much. That's the answer I'm looking for. Answer I'm looking for. Intermodal dispersion in simple terms. Different race or different modes. Arrays and modes the same. Let's say different race. This means different parts. 5 marks is this. Question different parts.
That's a question.
Just a minute. Means different TOAs. Time of arrival at the receiving side means post-broadening intermodal dispersion. Question. Answer today.
Okay, so yakangofanana chromatic dispersion.
I don't know. You tell me. Is it the same? Is it the same? I don't know. Is chromatic
Okay.
dispersion and intermodal dispersion the same by definition? If you know the definition of those two, and if you tell me they are the same, well, I don't know. You tell me. I don't know.
No, confirm.
You need to confirm.
Mm.
Confirm what? What do you know? Are they the same or they are not the same? You tell me.
Naona kunge zvakafanana.
Well, we'll see. There's a chromatic dispersion, and we'll compare the two. And if they are the same, we make your confirmation, madam. Okay. All right.
Okay, thank you.
Intermodal dispersion, different rays. I'm conflicted here. Is it different rays or modes? Are rays and modes the same? Choose correct but by definition. In I'm not so sure anymore. But I'm feeling it's modes because rays was totally something different. Different modes, different parts. I'll go with modes. Different times of arrivals. We have intermodal dispersion. All right. What do we mean by that? In an optical fiber, there we have our optical fiber. This is the core. This is the core of the optical fiber. What happens when we have multiple modes? When we have multiple modes, one mode, zero. Another mode, zero. Another one, zero. and so on and so on. Those are multiple modes in an optical fiber. Now, what happens? Explanation, brief, deep, more videos. So basically what happens, we have another mode. Let's put it in black. Wrong and straight like this. You have that one. Blue. Right. So basically what happens, the time, we have different modes. Don't understand. Second thing, Chata mentioned, we have different parts. My different modes are they're obviously taking my different parts, go to the transmission side, go to the receiving side. Yellow, router part yayo, red part yayo, blue part yayo. Dopane, different parts. Next, we have different times of arrival at the receiving side. Time in otor wane yellow ear. Kutirishike kunoko. The time in otor wane ear. Kutirishike up. Yakasiana. Time in otor wane this one is much shorter. Why? Less distance traveled. Pakata papana different parts to consider with different distances traveled. Where are we in Africa? Different distances traveled by mode. My mode that travel my distances akasiana. Wave relo iriri. This one. Parisha bamba parozogero. Iru travel a distance yakawanda. Travel a distance yakawanda. Logically, it means it will take more time to reach Kuno. But not the Skakunok, or a Blake here, most definitely in Graska. And Pasnos end up not detect what. It's no fun when there's a sort of chin one. Was send a pause Kuno. Pause Kuno go to fun or Ragada. Ragada saw. I'm going to pause it when no shika. A ring where also terra, also batana or whatever it is. Meet yourselves. What is that? Chief. One. And the effect of having these multiple modes, they could panic a post broadening. Panosika, I need the rubber eraser. Panosika mode rectangle, postcarunga mode, postcarunga mode, postcarunga mode, postcarunga mode, postcarunga mode, postcarunga mode, postcarunga mode. Pulse radar and grato shikara totally different on the other end. That is what intermodal dispersion is. Intermodal dispersion is pulse broadening, which is caused by different modes taking different parts in an optical fiber, meaning they will travel different distances, meaning they will have different times of arrival at the receiving end. Different TOAs means we have intermodal dispersion. Question here, in around 6 marks, you need to explain this, not paragraphs necessarily, but this and obviously the diagram. Okay, so my equations they pop up. I'm going to put 1 mark extra. No 7 marks for question 6 marks. I love doing this job. Didn't seem sick. I love that. I really and fun also one decision. Didn't seem sick. I can choose. Sometimes I do actually. Could memory takadi aga invite my scattering course yang. Don't go back 3 marks. Mark 3 marks, 5 marks. I can do that. That's why you need to participate. Really, seriously. That's why you need to participate. Because once I know your name, once I know you participate, I just feel obliged. Like memory tagadi or for my scattering. No, she should not fail. I can do that. The same for that question. If you convince me to lose, I can give you 8 marks for question and 6 marks. Yeah. Yeah, guys, I will deny it, obviously. But I'm telling you, I can do that. And that is intermodal dispersion, and we are done. It can be calculated. Intermodal dispersion can be calculated. We go that pause broadening. No, let me do this. Delta T. We calculated that as, we called it time difference. This is time difference. And I said it is the time difference of the first mode on the receiving end